Hello and welcome. Today we're going to look at part 4 of chapter 19, Oscillations. Firstly, we'll look at frequency and angular frequency of a simple harmonic motion. We've already discussed how we can illustrate a simple harmonic motion, especially my displacement time graph, as a graph that takes the shape of a sine graph. So what we see here is that as I release the object, it accelerates to the equilibrium position, then it decelerates to the maximum point over there, then it accelerates back to the equilibrium position, then it decelerates again to the point of our maximum positive acceleration, and that can be illustrated in a circle. So we know that our frequency is 1 over our period. But since we have a cyclic shape, we can also represent this in terms of angular frequency. And from chapter 2, you would be able to recall that the angular frequency is twice pi times the frequency. So this is the angular frequency, and therefore if we combine the two formulas, we can calculate the angular period, or the angular frequency in terms of period, or we can calculate the period in terms of angular frequency. Now this value is going to become very important very soon. Next we'll move on to equations of simple harmonic motions. So to go to the first part, when we want to calculate the displacement, we will say that the displacement is equal to the maximum displacement sine angular velocity times the time. So using this, we can now take any point on my graph, let's say at time 2 seconds. Okay, if I want to know where the displacement would be at that particular time, I take my original displacement and I times it with sine the angular frequency times t. Now please note we said that the angular frequency is 2 pi and the frequency. Okay, since we're working with 2 pi, we're working with radians. So the angular frequency is in terms of radians. So therefore you must put your calculator in rads. Okay, otherwise your calculations will be wrong. Okay, so we can write this in terms of a sine graph, but if we think in terms of a sine graph, this is where the displacement starts at 0. Now, I can never make something start from 0 in real life. I have to, if it's in terms of a pendulum, I have to pull it up to the maximum displacement. So oftentimes, we also get the same equation written as x0 cos omega t. Okay, so that would be the cos graph, and this would be the sine graph. And this one is when you start from the maximum position. This is where the starting position is graphed from the equilibrium position. In real life, we will always start from here, but they can sometimes give you the alternative graph. So next, we'll jump to the acceleration graph for a specific reason. So here is the sinusoidal displacement time graph, and we've said that its formula is x0 sine omega t. Okay, so as you remember when we did the graphs, our acceleration time graph is 100% out of sync with our displacement time graph. So therefore, our acceleration is directly proportional to the negative displacement, and that's actually the definition of a simple harmonic motion. A simple harmonic motion is when the acceleration of an object is directly proportional to the displacement, but in the opposite direction. Okay, so from this we get the formula that A is equal to negative omega x. But in this case, the angular frequency is squared. Okay, so we can already see that the angular frequency is in both those calculations. So we have seen now that our velocity time graph is 90 degrees out of phase with our displacement time graph, and our acceleration time graph is 180 degrees out of phase with our displacement time graph. So from this we get to the equation that our velocity at any given point is the maximum velocity, and then because it's 90 degrees out of phase, cos omega t. Okay, so because this is sine and this is 90 degrees off, this is cos. If this was cos, like the previous graph I showed you, this one would be sine. So it's based on that. So this equation is what I use if I have the velocity time graph and I don't have any values of the displacement. But in terms of displacement, we can also calculate the velocity. So we can say V is equal to plus or minus omega, and then the square root of x0 squared minus x squared. So the position at which you find your displacement at any given time squared is subtracted from the maximum displacement squared time, so it's square rooted and times with the angular frequency, and that gives us our velocity. Now we can calculate our maximum velocity with this. So when we have max velocity, okay, when my velocity is maximum, my actual displacement at that stage is 0, so that becomes 0. So then it's going to be the omega, the square root of the maximum squared is going to be x0 squared, and then we can calculate our maximum velocity. So this is when we go in terms of that, okay, but this formula relates to the graph. So when we have values from the displacement, we can calculate the velocity, or if we have the velocity time graph, we can calculate the velocity.